Hello everybody, this is Notes 26 and we're going to finish talking about the chain rule, and we're also going to learn how to find the derivative of an exponential function. And I'm not just talking about e to the x, but with other bases such as 2 to the x, 3 to the x, 10 to the x, etc. And then of course also incorporating that with the chain rule. So in the first slide here, what you're going to see is the development of the idea of how we get the derivative of exponential functions. So problem number 1, we have y equals e to the 4x, and we can use the chain rule to find the derivative. So remember from yesterday, if you have e to the something, then its derivative is e to the something times the derivative of that something. So in this case, e to the 4x times the derivative of 4x, and the derivative of 4x is 4. So our answer is y prime equals 4e to the 4x. Okay, same idea for problem number 2. We have y equals e to the something, and so we're going to find the derivative by just having e to the something times the derivative of that something. And notice the exponent, what I'm calling something, is x times natural log 10. Well, natural log 10 is just a constant, like 4 was in the first problem, so x natural log 10 is just some number times x. So just like the last one, we have e to the something times the derivative of that something. The derivative of 4x was 4, the derivative of 5x would be 5, and the derivative of natural log 10x is natural log 10. Whether you put the parentheses around the 10 or not doesn't really matter. Okay, now let's use that idea to move on to number 3. So this time I'm interested in finding the derivative of an exponential function that doesn't have base e. Well, here's the problem. We don't know how. We know how to find the derivative of a function that does have base e. So what we're going to do is find a way to manipulate this and make it look different, still equivalent, but look different, so that it has a base of e. So let me remind you that we have infinitely many different special forms of 10. For example, 10 over 1, 20 over 2, the square root of 100. These are all special forms of 10. Here's another special form of 10. E to the natural log of 10 is a special form of 10. The e to the power function cancels with the natural log function, leaving you with just 10. So what I'm going to do is write the function as y equals e to the natural log 10, that's replacing the 10, raised to the x power. And remember, if you have a base to a power, you can multiply the powers. So we can multiply the natural log 10 and the x. So we have y equals e to the x natural log 10. Now, this is the same problem we just did, number 2. And we know how to find the derivative of that using the chain rule. The derivative of e to the something is e to the something times the derivative of that something. Now what I want to do is actually rewrite this, going back to having a base of 10. So let me go backwards and think of e to the x natural log 10 as e to the natural log of 10 to the x. And then go backwards one more time and remember that e to the natural log 10 is the same as 10. So this is not the process you're going to have to go through every time. This is the process we go through once or twice until we figure out the pattern that's going on. And then we use that pattern, we make a rule for it, and we move on from there. So let's look at one more example. Let's do y equals 2 to the x instead of 10 to the x. But the same idea applies. Let's rewrite the function as y equals e to the natural log of 2 to the x. And that's the same as, guess I don't need those parentheses, e to the x natural log 2. Find the derivative. The derivative of e to the something is e to the something times the derivative of the something. And then remember that e to the x natural log 2 is equivalent to 2 to the x. So our derivative is 2 to the x natural log 2. Okay, when we were finding the derivative of 10 to the x, we got 10 to the x natural log 10. when we were finding the derivative of 2 to the x, we got 2 to the x natural log 2. So do you see what's going on here? And you can even apply this to y equals e to the x. Its derivative would be e to the x times the natural log of e, because the natural log of e is just 1, so that's still going to be e to the x. Okay, so let's see if on the next slide I have that written out. There we go. Okay, in general, if y equals a to the x, a has to be, the kind of base that's acceptable for an exponential function. So a has to be greater than 0, a is not equal to 1. Then the derivative is a to the x times the natural log of a. So that's another one to memorize. Now, unfortunately, your book doesn't really give you a lot of practice with this particular derivative rule. So for your homework, I'm going to tack on a few extra problems to the book problems, and hopefully in your notes you can make this really stand out, because what I find is students forget about this one. It seems like it's not used that often and the book doesn't require much practice with it, and next thing you know, we've moved on to other things, and then eventually it's hard to remember this. So do something to make it really stand out. Okay, for some practice problems, let's find the derivative of y equals 7 to the x. All right, we'll just use the rule. It's going to be 7 to the x times the natural log of 7. You don't have to go back to the drawing board and rederive it. You just use the rule. Use the new shortcut, basically. Number 6. So now let's make it more interesting, and let's combine that rule with the other rules we've been doing. For example, let's combine it with the chain rule. So here we have a function inside a function. We have the sine of x function as the inside function, and it's inside the 7 to the power function. So let's take the derivative of the outside and multiply it by the derivative of the inside. So the derivative of the outside, 7 to the something, times the natural log of 7, now times the derivative of the inside, and the derivative of sine x is cosine x. Now, I suppose a person could rearrange these terms and maybe write cosine x first, and then 7 to the sine x. I don't know that it really makes a difference for this particular problem what goes first, second, or third. I don't think you want to write natural log of 7 before 7 to the sine of x, unless you make it very clear that you're multiplying there. So no real hard and fast rule about that. Sometimes students want more concrete advice about what to do to simplify the answer, and sometimes in this level it's just not there. There's shades of gray. Okay, number 7, we have 3 to the x as the inside function. It's inside cotangent of x, and it's inside secant of x. So we have 3 layers to the chain. So let's start with the derivative of the outermost layer. And the derivative of secant something is secant something tangent something. So secant of what's inside times tangent of what's inside. Make sure you put that inside in both of them. Sometimes students will write this. They forget that the argument, the inside part, has to go into secant as well as into tangent. So that's the derivative of secant. Now we move on to the next layer, cotangent, and its derivative is negative cosecant squared something. So negative cosecant squared of the inside. And then we move on to 3 to the x, and its derivative is 3 to the x times natural log 3. So when we look up and down our answer and we look for ways to simplify, technically we should take our constant and bring it to the front. So I suppose that would be the negative and then also the natural log 3. But it hardly feels worth it, honestly, to rewrite the whole thing and risk possibly making a mistake in maybe missing something or writing it wrong. But technically speaking, if we're simplifying, we're supposed to have the constant multiplied by any other constant that happened to be in the problem, and put in the front. Okay, so hopefully I got everything there. Looks pretty good to me. Actually, it looks horrible. That's a very scary answer, but I don't think anything is missing. Oh boy. Okay, I think this is going to do it for us. So how many layers do we have here? 1, 2, 3, 4, 5. I would recommend challenge yourself, pause the video, find the derivative, and then compare your answer with my answer. So, starting with the outermost layer, tangent, its derivative is secant squared. So we have secant squared of the whole inside. Close, 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 close. I think there's 4. Times, now we have sine, and its derivative is cosine. Cosine of its whole inside. Close, close, close. Times, now we have secant, and its derivative is secant something tangent something. So secant of its inside times tangent of its inside. Not even going to have enough room to write this across the screen. Times, and now we're on to cotangent, and its derivative is negative cosecant squared. So negative cosecant squared of its inside times the derivative of 2x is 2. Wow. Now, each of these things has a different inside. That's different from this, and different from this, and different, well, these are the same. And this different from this. So it's not like we can combine these together. The only thing we could do is take the 2 and the negative. That gives us negative 2 for our constant and write it in the front. So, okay, I'm going to be strong. I'm going to do it. Negative 2. I'm not going to say it all out loud, but you get the idea. Hopefully, I don't miss out on any of the parentheses or little details along the way. We have to pay close attention to detail. We want to understand the big picture ideas, but we also need to be accurate with the details. Both of those things make you a fine mathematician, and this is the last one. Okay, that was good practice remembering the derivatives of lots of the trig functions as well, and sometimes we tend to forget those. All right, so for your assignment, some problems out of the book. These are going to be the chain rule problems, and they're a little bit more advanced than the ones you did yesterday. And then I've added these 3 extra problems here at the bottom so that you can practice with your exponential derivatives. Thanks, everybody.